our last section is 3.4, and we'll do it today and tomorrow, so I'll throw the big old A up on there. And they call it exponential growth and decay. But really, we're just kind of solving some exponential equations is really all that we're doing on this one. So we've been looking at those exponentials, right, and also looking at those logarithms. So last year, in the last lessons, we were just kind of looking at those power properties, the product property, the quotient property, you know, either expanding them and contracting them and all of those. And we wanted to make sure we had a nice little good handle on all of those rules, so then when it came to today's, where we're actually going to solve some of those equations, we can use some of those properties. So we're going to look at some exponential equations. I didn't miss the glasses fogging up though. All right. So I think I have, I don't know, about four different like examples for us to kind of go over. So let's say we had 2 raised to the 3x minus 8, and we said that that was equal to 16. So when it comes to our cute little equation, we always want to solve for our variable. But the problem is our variable is like up here in that exponent, right? So we got to try and figure out what we're going to do with that little x up there. So I like to sit there and think of if I can get to where my bases are exactly the same. So let's say I had, you know, a base and I wanted that to equal some other base. And as long as my bases are the same, if I know whatever my exponents are, I know that those babies got to be equal. So I know that m has got to equal n, right? So like if I said, like really simply, like if I had x to the 6th and my base was still the same, so my base is that x, like in order for those two to be equal, what does my exponent have to be? It's got to be 6, right? So if I can get it to where my bases are exactly the same, then I know that my exponents have to be equal. So when I look at my cute little problem over here, my base is 2, and then my base on this one is 16. So right now they're not the same. So I gotta try and make them the same. So I usually look for the smallest number, 2. Right? So is there a way that I can write 16 so that it is actually 2 raised to some exponent? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So can I write 16 as 2 to the 4th? Yeah, it's still 16, right? And then I have my left side, which was 2 to the 3x minus 8, right? So now that I know that my bases are exactly the same, what do I know about these exponents? Well, then now my exponents have to be equal, right? So then I know that 3x minus 8 has to equal 4. Nice little easy equation, right? What are we going to do? Add 8 to both sides. So we're going to get 3x equals 12. Divide by 3, and we're going to get x equals 4. Right? So our goal right now is to always figure out a way to get our bases to be the exact same numbers, because once those bases are the same, we know then that our exponents got to be equal. Right? Fancy it up a little bit? Yes, I can leave it on here. Why not? Let's say we have 27 to the x plus 3. And let's say that equals 9 to the x minus 1. So our goal is to get our bases to be exactly the same, right? So what do we want to maybe think about trying to make our base? We could try and make it a 9. Right? So I got to figure out if I can get to 27. So 9 to the first is 9. 9 squared is 81. Well, that's not going to work, right? Because we need to get to 27. Anybody think of any other number we could try? 3. Let's try 3, right? So if I want 27, right? 3 to the first is 3. 3 squared is 9. What's 3 to the third? 27, yeah. So we can write 27 as 3 to the third. And we can't forget about our little x plus 3. So in parentheses, I'm just going to put my x plus 3 equals. So can we do the same thing with 9? Can we write 9 as 3 to something? Yeah, that's 3 squared. Then I still have my x minus 1. Are my bases exactly the same? Yeah. So what do I know about my exponents then? They have to be equal. So what do I have? I have 3 to the x plus 3 equals 2 to the x minus 1. Okay. Do some fancy algebra. Use our little distributive property. 3x plus 9 equals 2x minus 2. I'm going to subtract 2x from both sides and get x, and then I'm going to subtract 9 from both sides and get negative 11. Okay. If I just did 2 steps in one. Not too bad on those? Think you guys could practice? Yes?
So you keep saying that like the exponents have to be like equal?
Yep.
When you say that, does it just mean when you solve for x, you have to have a whole number?
Well, if they're equal, you're just, whatever your exponents are,
Just equal to
yep, they equal each other. So you're just putting an equal sign in there. And then solving it for the variable. Yep. Because if you wanted to check it, well, if I put in negative 11, right, and for my x, well, we'll do it on that one and it'll come out the same, right? Negative 11 plus 3 times 3. Or if I do negative 11 minus 1 times 2, I'm going to get the same number. Yep. All right. So our goal is to get those those bases to be exactly the same, right? But guess what happens in life? Sometimes our bases are not the same. Right? So let's say we had 4 to the x equals 15. So can we think of a number that's going to get these babies to be exactly the same, the bases to be the same? No, because 15, there's no base that we can raise that to get 15, right? So this is where our logs and natural logs and our power property or power rule come in handy. Remember, when it comes to an equation, any equation, whatever you do to that equation, as long as you do it to both sides of the equation, you're not changing the equation at all, right? I can multiply both sides by 5, and it's not going to change what my answer is going to be, my outcome is going to be, right? So the same thing happens with like logs or natural logs. If I multiply both sides by a log or a natural log, I'm not changing the equation at all because I'm doing it to both sides, right? I'm still keeping it equal. So we're just going to use natural log because it's a little easier to handle because you don't have to worry about it. I'm going to take the natural log of both sides. Right? So I'm just going to take the natural log of 4 to the x equals the natural log of 15, right? And then now when it comes to all of those rules we learned, there's something about a power rule. And the power rule, what did that say? Whatever our exponent was, we could simplify it, right? We could take that exponent and we could bring it out to the front, right? So my 4 to the x, when I take the natural log, by using that power rule, I can bring my x out front. So then now I have x times the natural log of 4 equals the natural log of 15. And I'm trying to solve my equation, so I'm trying to solve for x. So anybody got any ideas how we can get x all alone? We can, yeah, divide by that natural log of 4 on both sides, right? Natural log of 4. Those babies are going to cancel, right? So we're going to get x equals the natural log of 15 divided by the natural log of 4. We can jump on our fancy dancy handy dandy little calculator, right? Or on Desmos and plug those in. And I think you get like approximately 1.16. Right? And everybody found those cute little natural log buttons on their calculators or on Desmos. Right? Everybody from yesterday or last year, last lessons. All right. One more kind of along this same little line. We got to keep building, right? We got to keep, you know, getting more and more fancy. So let's say we had 40. Remember E? Let's throw E in there. 0.6x equals, oh, hold on. Let's get really fancy. Let's then subtract 3 minus 3 equals 237. Just to get it all wild, crazy, and fancy, right? So when they give us a whole bunch of junk, because we know that we're trying to figure out what our x is within that exponent, so we want to try and simplify it down as much as possible before we try and figure out what's going on with our x. So I'm going to like add 3 to both sides. Okay. So then I'm going to have 40 e to the 0.6x equals 240. Right? And then I have e raised to the 0.6x, and I still got that 40 out front, so I'm going to try and get rid of that 40. And we're going to get rid of the 40 by dividing both sides by 40. And then now I'm down to e to the 0.6x equals 6. Right? So now I have my little exponent kind of all by itself with that e. So I know that I probably can use some little power property, right? And when it comes to e, I can take the natural log of both sides, right? So I'd have the natural log of e to the 0.6x equals the natural log of 6. Do you remember what natural log stood for? It was a log with a very special base. Is this the same thing as log base e? Right? So if I wrote it as log base e, and I just look at this e to the 0.6x, right? We're just going to focus on this a little bit. I can actually simplify this down. If I were to take this and try and turn it into an exponential, right, so it's got to equal some little guy. So when it comes to writing these as exponentials, your base was e, right, raised to whatever this guy was. Remember, that was your exponent. That's your exponent. equals your number, which would be e to the 0.6x, right? So does my little box have to equal that 0.6x, right? Because my bases are exactly the same, and if my bases are the same, then I know my exponents are the same. So anytime you take a natural log of e, your answer is always just going to be whatever is that exponent. So I can take, when I take the natural log of e raised to the 0.6x, that's going to simplify down to 0.6x equals, and we still have our natural log of 6. And then to solve it for x, what am I going to do? I'm going to divide by 0.6. And I don't know, I think we get something about like a 2.99. That's my guess.